and then in particular we also did the calculation which was first done by Debye in this context, and we understood his approximations, and we also understood therefore that why this A might not come out correctly from the calculations, but this T cube is still universal. So that was something that we stressed quite a bit. Okay, and then from here we quickly went to another system which was a gas of photons at equilibrium. And then we saw that we could essentially use whatever we did here, but with certain key differences that we pointed out also here. Okay, so that was one. Then in these kind of systems we also calculated the number fluctuations both for this phonon gas and the photon gas, and we realized that even if in a certain mode the average number is very high, nonetheless the fluctuations do not decrease. So the numbers fluctuate a lot in this system, and therefore they are different from a bosonic system which has a, let's say, a fixed number density. Okay, then we in fact went to such a bosonic system which had a fixed number density, and we in fact yesterday understood this phenomenon. Okay. So we did all the calculations to understand this BEC for a system of free bosons, let's say with a given number density, and we in fact calculated the critical temperature below which such a thing happens. Then I briefly told you, but very briefly because that's a bit technical, what happens if you put some small interactions on these bosons, and then in fact when you condense into such a state, you also naturally get something else which is very interesting, which is called superfluidity, which of course you don't get in a system of free bosons. Okay, good. So that is where we stopped yesterday. So also I gave you 2 homework exercises. So if you haven't done it, I encourage you to still do it, and then we may discuss it in the afternoon, right? It's for your own benefit. Okay. So now, are there any questions?
Just a parenthetical remark about the history. Phonons and photons. So of course Planck presented his law in 1900, but there were many attempts to improve it.
Correct.
1905 Einstein,
and
then 1911 Debye.
That's correct.
So he, in some sense, he had thought about photons and
yeah.
And so the Debye model was in some sense natural extension.
Exactly. That's correct. Yeah. We in fact discussed a bit of that. Yeah. But are there any questions about anything? Okay, good. Okay, let me see. How many people have attempted those 2 exercises? Raise your hands, please. Okay. How many people have succeeded in calculating the things? Succeeded. Oh, you have succeeded. That's okay, but okay. Partially succeeded. Okay, good. That's fine. So in the afternoon, we can discuss those 2 problems before I start on something afresh. So good. So in today's lecture, my plan is to dwell a bit deeper into some of the things which PK has been already discussing, and in particular I'll take the 1D and the 2D Ising model as concrete examples. Okay. So yeah, in this lecture we'll go back to sort of some well understood classical models. One can do whatever I'm doing even with quantum models, but then the analysis just becomes a bit more complicated, and whatever insights we have to get, we can get from the simpler analysis. So I'll just stick to that. So what you have been hearing from PK very nicely is that when he introduced this transfer matrix approach and these eigenvalues of the transfer matrix, then he showed that for 1 dimension, for short range Ising model or even some generalized Ising models, you cannot have a phase transition at finite temperature. That's what you saw, right? But today we are going to also see the effects of increasing the dimension. and then we'll actually see that there is this phase transition at a finite temperature, and there are very interesting properties associated with that. And we'll also try to get some exact numbers as we go along. Okay, so this is a very rich subject of phase transition. So I thought I'll mention some broad things first, and then I'll start with particular examples. Okay, so that's the plan. Good. So let me just show a few slides, and then I'll go to the board again. Okay, so till this point we have understood. So let's not talk about Bose-Einstein condensation. So good. So we know, as we have discussed over the course of the previous lectures, we know that matter exhibits different phases, and in equilibrium these phases are characterized by well-defined macroscopic properties. So one thing which was also stressed previously is, when you have phase transitions, then the two phases on different sides of the phase transitions are actually distinguished by macroscopic properties, right? That's important. I mean, you don't need to really go to a microscopic detail to understand that this is phase 1 and this is phase 2. That was already highlighted, right? So of course, you know various examples here. I'm sure you can guess whatever the pictures are here. Certain phases are more exotic, like that of this superconductor, right? Many of you may have seen this experiment. Some of you may have even done this experiment yourself, right? Then of course, there are quote unquote more mundane looking things like a magnet or a bar magnet which sticks to a fridge. But as I already told you, I mean, actually the fact that you have a bar magnet sticking to a fridge is a highly quantum effect. There is no way you can explain it classically, okay? So that's actually a remnant of quantum mechanics at room temperature. Okay, and so on and so forth. So of course, you know, for example, you consider a liquid versus you consider a gas, then there are obvious macroscopic properties which are different. For example, this solid is rigid, right? But of course, if I open this bottle, and I won't do it, and do this, then of course I'll see that this liquid will flow, right? So there's a clear macroscopic difference, okay? Now the important thing is, which we also know from sort of experience of looking at these phases all around us. So the very important fact is that typically as you lower the temperature, as you go to very low temperatures or low temperatures, very low, low, these are all subjective terms. The scales depend on the problem you're looking at. Then as you go to low temperature, the states that you get or the phases that you get typically have less symmetry than that of the interaction Hamiltonian. So this is a very crucial fact, that these states have less symmetry than that of the full Hamiltonian, okay? Full Hamiltonian through which the constituent particles are interacting with each other. Good. So we'll try to understand this and certain other aspects in our discussion of phase transitions. Of course, feel free to ask questions. Okay, so one example which we have already discussed a couple of times during my lectures is that of a crystal, right? Of course, we didn't discuss the crystal itself, but we discussed things like specific heat, its excitation, so on and so forth. So if you just sort of take a snapshot of an idealized crystal, which may look like this, and you take a snapshot of, let's say, some liquid state made of the same atoms or molecules, you will see a clear difference. In the liquid state, the atoms would be arranged in a more or less random pattern. Of course, random does not mean that the dots would be completely uniform on the plane of whatever paper, right? As we have already seen in earlier lectures. But if I sort of bin the things reasonably, one can see that things are more or less random, bin the positions and so on and so forth. Okay, but clearly this kind of a crystal is not at all random. It's some highly ordered structure. It's some highly ordered structure. And there's a crucial fact here. So if I look at this crystal, then let's say I take this picture and I don't want to change this picture and yet do some operations on it, then I can only do some discrete translations and discrete rotations by some angles, right? Otherwise, whatever else I do, this picture will change, right? This I hope is clear to you, okay? But of course, we know that the underlying Hamiltonian of whatever the interaction between the atoms is, etc., must preserve all translation symmetries and must preserve all rotation symmetries. I mean, that's the property of the interaction between these atoms, okay? At least if these atoms don't have some complicated internal structure which gives some preferred directions or something, right? So in some reasonable atomic system, the interaction Hamiltonian will preserve all translational symmetries and all rotational symmetries, right? But clearly the crystal breaks them, right? And again, as I said, there are obvious macroscopic consequences of that, right? So that's important. So for example, some of the consequences are again immediately seen. You might have seen many natural crystals in museums, for example, right? So normally if you see a crystal or if you deal with a crystal or you ask anyone who deals with a crystal, it's always easier to cut a crystal along certain planes, right? So you take a crystal, you just try to cut it. You'll see that it's easier to cut it along certain planes. That's a consequence of the fact that this is some highly ordered pattern with certain well-defined high symmetry directions and other directions which don't have that much symmetry, okay? Similarly, when you see natural crystals, typically you see that it's not like some random weird structure. I mean, if you look at the surface, you can see very interesting typical angles and so on and so forth, right? So you can just see this image. You can see that there are certain very well-defined angles, right? And this internal pattern which appears at the surface of the crystal is also a consequence of the fact that this is a highly ordered structure, right? So these are all simple macroscopic consequences. And thirdly, as we discussed sort of briefly, actually not so briefly, is given the fact that something is a crystal, it actually tells you immediately about its low-lying excitations as well, right? So the low-lying excitations of a crystal, no matter however complicated it is, are linearly dispersing phonons. So that's important, right? So we even saw an experimental example of that, right? So see, this guy, this is some experimental phonon dispersion curve of germanium. See, this is highly complicated, right? There's so much structure here, but the low-lying excitations are nonetheless linearly dispersing excitations, right? And that's exactly what gave us this T cube, and that's why this T cube is so robust, okay? So that's important to keep in mind, right? Okay, so I hope this is clear, right? So not only the fact that it's a crystal and breaks certain symmetry, not only does it tell you about zero temperature physics, it tells you also a lot about the low temperature physics. That's important, okay? Good. So now we'll talk about phase transitions, right? So this is a picture which you have seen earlier as well, right? So we have already been introduced to the Ising model, right? So I don't need to explain this again. Just a small comment about the notation. Whenever I use these brackets, this signifies nearest neighbors, right? So I think PK was using the notation I and I plus 1. This symbol just means that I and J are nearest neighbors. So it can be a 2-dimensional lattice, it can be a 3-dimensional lattice, whatever, but the symbol means that they are nearest neighbors. That's it. Okay, good. So he also talked about Monte Carlo simulations. So these are just some spin configurations generated on the Ising model. Remember in the afternoon yesterday, right? You discussed, yeah. So in the afternoon yesterday, he discussed about the metropolis dynamics, right? So this is actually simulation done using the metropolis dynamics, which he wrote down on the board. And basically this simulation is done at some low temperature. This simulation is done close to the critical temperature for the 2D Ising model, and this is done at a high temperature, okay? And for the 2D Ising model, this number where the phase transition happens is known exactly, and this was due to a beautiful work done by Onsager in 1944. He basically solved the partition function of the 2-dimensional Ising model exactly, and that actually helped to resolve many things which were highly controversial. I mean, people were very confused about whether there is some notion of a spontaneous symmetry breaking and does it at all happen in a realistic system, so on and so forth. And Onsager's exact solution actually laid all that to rest, and he showed exactly that, look, this is an example where there is spontaneous symmetry breaking at finite temperature. So there is no way that you can argue with it, right? That's it. Good. But this is a very subtle concept. That's why so many people were confused. Okay. Now we might think it's completely obvious, but yeah. Okay. Good. So the crucial point is the following. Suppose I go to low temperature, then the description is very easy. So this black, imagine, is downspin, and this white, imagine, is upspin. Then you see at low temperature the description is very easy. Mostly the thing is black, and there are some small patches of white there. So it almost looks like the night sky here, but that's by accident. So of course if you raise the temperature a bit, but you're still on the low temperature side, then these white spots would sort of start becoming bigger, and they'll have some interesting size distribution, but still they'll be more or less finite. Okay, and that length scale would be given by some correlation length of the system. Now on the other hand, if you go to the high temperature side, you can more or less see what's happening, that this picture is completely random sort of mixture of black and white, and that's what the spins are doing. If you go to any point on the lattice, then basically there is uniform probability of seeing it to be up or down if you are at reasonably high temperature. However, if you come close to Tc, then you see some very interesting structures emerging. So this is the snapshot of a spin configuration at a temperature close to Tc. So then what you see is that, so these are called domains if you wish. Okay, so you can see that these domains of black and white, so have some very interesting size distribution. There are some very small domains like here. There are some slightly bigger domains like here. There are other things like that. There are even bigger domains like here. Then there are even domains which are very big, right, like here. But see, even in a big domain, it's very important to stress that there is a lot of substructure inside. See, in this black thing, it's not that this is completely black. If you go inside this black thing, you will see that there is this white and so on and so forth. So if you could do a really big lattice in a Monte Carlo simulation, that's of course difficult, but if you could, then you would see that if you're exactly at Tc, you would actually see some sort of a fractal structure. Okay, so you take a domain and you sort of zoom in into that domain, you will see more substructure. You zoom in more, you will see more substructure, so on and so forth. So this is a rather interesting and a complicated state, and you might wonder, okay, is it useful at all? But we'll soon see why it's very interesting. And another thing which I would like to stress is this notion of a spontaneous symmetry breaking. So, okay, so this was already discussed in class. The Ising model, this model for example, if I don't put a magnetic field, so let's say there's zero magnetic field, then this model has a symmetry. The symmetry is simply that if you change all the variables Si to minus Si, then the Hamiltonian stays the same. So this is, if you wish, a spin inversion symmetry, and the paramagnetic state actually preserves this symmetry, whereas the ferromagnetic state, oh, okay. Use headphones. and the where am I? And the ferromagnetic state actually spontaneously breaks this symmetry. Now this is actually an unusual thing if you think about it, and we'll actually come to the sharp definition. Switch off your mobile. Or anyway, right. Okay, so this ferromagnetic state breaks spontaneous symmetry, breaks the symmetry of the Hamiltonian spontaneously. So this S to minus S symmetry, whereas the paramagnetic state does not. See, it's even clear from this picture, right? There's predominantly black here, right? And basically, even if you wait a long time, if you have a really big system in your Monte Carlo, and you start with predominantly black below Tc, you will stay predominantly black. That's the meaning of spontaneous symmetry breaking. So this is actually a subtle concept, and we'll spend more time in explaining it over the board. Okay, so good. Let me actually say something here which is important. This is the following. So suppose I just look at this Ising model, right, on the square lattice. So let's just look at the Ising model on the square lattice. So there are some spins interacting like this, so on and so forth, and this is the Hamiltonian, right? Now, some of you may know, or maybe most of you know this, that the square lattice is something called a bipartite lattice. So what that means is the simple statement that suppose I mark this side as A. Okay, I just call this side as A. And then I say that its nearest neighbors, I call all of them B. Okay, good. So let me call, so there are 4 nearest neighbors, right? I call all 4 B. Then I just repeat the thing. See, now B has its nearest neighbor to be A. So I want to be self-consistent, and I just mark all the other 3 neighbors of B to be A, right? So I do this. Now I do the same here, and so on. Right? So in this way, you can see that you can cover the entire lattice, and the sides sort of get divided into sides which are type A and sides which are type B, and A only has nearest neighbors which are labeled B, and B only has nearest neighbors which are labeled A. Okay, this is the property of this lattice. It's also the property of the cubic lattice in 3 dimensions, right? So this is called the property of bipartiteness. Okay? Not all lattices are bipartite. One simple thing that you can try to do in your home is try to see whether you can do it for, let's say, a triangular lattice, right? Try to cover the triangular lattice like this with just, okay? So the rule is again the same. I put an A here, the 6 nearest neighbors I cover with B, and I keep on doing the same. Try to do it for the triangular lattice. You will see that there will be some problem. Then you try to do it with more variables, let's say A, B and C. Then you try to see if you can do it, so on and so forth, right? Good. But this is clearly a bipartite lattice. Good. Now let me do some simple jugglery. This is a ferromagnetic model, right? Because there's a minus sign here. Okay. Now let me do the following. Let's say I do some variable transformation like this. For all the spins which live on the A type points, I just let them be whatever they were before. For all the spins which live on the B type thing, I make them minus. So these are new variables. So let's put tildes here. Right? This is clear what I'm doing, right? I'm just doing some variable transformation. Given any configuration, I just adopt this rule and that's it. I can transform from this variables to this variables. Now why am I doing this? So let's go back and write the Hamiltonian in these variables. These are still Ising variables. Everybody is clear on that, right? Because if this is +1, -1, this can also only be +1 and -1, and yeah. If this is +1, this would become -1. If this is -1, this would become +1. That's it. But these are Ising variables. Okay, good. So then, let's look at what the Hamiltonian does. Clearly, in these new variables, the Hamiltonian is almost the same with a crucial difference. And the difference is that J has changed sign. Is everybody happy with this? The J has changed sign. So now this is an antiferromagnetic model, right? So this is an antiferromagnetic model. So that just means that the antiferromagnet on a square lattice or a cubic lattice would have the same critical temperature as that of the ferromagnet, just by this simple thing, right? Okay, good. So if you take an antiferromagnet and you cool it down, you should also see a phase transition to an antiferromagnetic state, where the spins are staggered, up, down, up, down, up, down. So basically, the spins would do something like this: up, down, down, up. So this is like a staggered pattern. of spins, right? Good. Now, this is an experimental fact, and there are also very good theoretical reasons to explain it. If you take sort of, let's say you ask your experimental friend that give me 100 different magnetic compounds. So you take all those 100 and you go home with them. Your experimentalist friend would of course be very unhappy with you. But then you will actually realize that most of those compounds are actually antiferromagnetic in nature, not ferromagnetic. Okay. However, it's an interesting thing that you know, ferromagnetism was known from a long time. I mean, it was known even long back in history in 600 BC or even before that. So it was certainly known in ancient China, it was also known in India and so on and so forth. Okay, good. So this was known that there are ferromagnets. But I said that in nature, most of the things are antiferromagnets, right? But the first experimental verification of antiferromagnets was in 1949. Then you should ask yourself the question, why did we have to wait for so long to see something which was all around us, right? So the reason I'm giving you this long detour into this is simply to say that just because you haven't seen something doesn't mean that that doesn't exist. Okay, so yeah, that's all. See, this is a very sharp statement. There are many more antiferromagnets in nature than ferromagnets. I mean, that's it. It's a clear statement.
7:1. I'm not sure.
Yeah, I'm also not sure, but right, yeah. Okay, so let's say 7:1. Whatever, but many more. Yeah, good. So the reason why we took so long to discover it is the following. So there was this explicit phenomenon, but we did not have a good experimental tool to probe it. See, when something becomes ferromagnetic, there is a very simple way you can sort of probe it, which also was done in the ancient times. That's how people realized this thing, that it attracts certain other metals towards it, and that you can see very easily, right? However, an antiferromagnet gets into such a kind of a thing, and then there is no sort of net big magnetization in the sample, and it cannot attract something else, right? But if you could see this structure on an atomic scale, then of course you are completely sure that there is an antiferromagnet, right? So the way it was seen was also very nice. I mean, so just let me spend 1 minute on it. So these two gentlemen, they did neutron scattering on a certain compound, which people knew would become people thought it would become an antiferromagnet. Okay, so this compound had a certain crystal structure. Okay, and then the thing below a certain sharply defined TC was expected to become a antiferromagnet. Good. So now you see the neutrons. When you scatter neutrons, of course, the neutrons can pick up the crystal structure, right? Because there is some regular structure forming. But the neutrons are also sensitive to the spin polarization. So in principle, they can also pick up the spin structure. So now suppose you're much above TC, okay? Then you get some rack peak like things here, right? And they signify the crystal structure. Now, immediately after you cross a certain magic temperature of TC, you see those peaks surviving, the older peaks, but you see newer peaks as well. Now, what is the reason for the newer peaks? The reason for the newer peaks is now there is the staggered magnetization here. So, if you just look at this picture again, see, one side of picture is if you are at high temperature, then you don't put any magnetization here. Then this side is equivalent to this side, right? There is no difference. But if you are below TC, this side is not equivalent to that side, because I said that neutrons are also sensitive to the polarization of the thing, right? So then clearly, if you become below TC, the periodicity of this structure changes, right? Because now you have to, if you wish, mark this side as white and mark this side as black, right? And then you think of the periodicity again. So that's it. That's why they actually could sharply see that when they went reasonably below TC, there are these newer well-formed lines which emerge, and these lines, and they signify this antiferromagnetic order, right? So yeah, that's something to just keep in mind. And is there, I think now I can go to the board. Let me just check. Oh no, this I can show later. Okay, right. Good. So with this sort of sort of background, we can now go into trying to understand phase transitions through concrete models, right? But any questions on anything? Okay, so the first thing we can ask is try to again look at this picture and ask something about this. So see, this also ties up with something which Mustansir was discussing. See, near the TC, I said there are domains of various shapes and sizes, right? In fact, there's a fractal structure, and that basically just means that there is a lot of fluctuation in the system. So remember, Mustansir was discussing about fluctuating response theorems, right? So what that means is, clearly, if you go near TC and you measure appropriate response functions, you will immediately see a divergence near TC and not anywhere else, right? So let's just elaborate on that statement a bit, right? So this is already something you have seen, right? So that's the first point I therefore want to raise. Okay, good. So let's see what kind of response functions we can think about these magnetic systems. So the two response functions we can think about these Ising-like systems are the following. The first response function is obvious. See, because there are these sort of fluctuations, that means that if I look at the energy fluctuations in my system, then I'll see a lot of energy fluctuations near TC. There's another interesting thing. So I'll tell you later, already you may have guessed that the order parameter here is the magnetization, but we'll see later what is the meaning of order parameter and things like that. It's good to define them properly, and yeah, not just talk of words. There are very precise definitions, okay? So once you define them, that's it. So, okay. So here the order parameterization can be thought of to be the sort of the magnetization per site, okay? So you know that the magnetic field couples linearly to this order parameter, right? Because if I just put on magnetic field here in this Hamiltonian, the term that I'll get, extra term that I'll get is of course apart from already this guy, right? So this is the extra term that I'll get. So then that means that the other response function you should look at is susceptibility, because that's del m by del h, and that response function will also already show you a big fluctuation near critical point. See, now comes the important thing about order parameters. See, I told you that for the antiferromagnet also there is a phase transition exactly at the same temperature if you take a bipartite lattice. We just proved it for the classical model, right? So now I can ask, suppose I look at the uniform susceptibility of an antiferromagnet, does it show any divergence near TC? The answer is no. The simple reason the answer is no is that for an antiferromagnet, the order parameter is not the total magnetization per site. That's not the order parameter. The order parameter is this weird object. Well, it's not so weird, it's just some. So what is the total magnetization per site? You just do this and maybe you divide by the number of spins in your system. For this kind of a thing, what you do is, okay, I need to put an alternating sign. I hope I got this right. Okay, so basically I need to do some kind of a sum with signs floating around, where basically with the A sites I'll have to associate a plus sign, let's say, and with the B sites I'll have to associate a minus sign. Why? Because of course if I do the total magnetization, basically I'll just get 0. But if I do this, right, then what am I doing? Let's say for all the A sites I put a +1, right, by my convention. And for all the B sites I put this thing to be naturally -1, right? Then if I have such a staggered thing, this order parameter will actually pick it up, right? And right. So then if you could in your experiment, even though it's very difficult, if you could in your experiment measure the magnetic susceptibility at this wave vector, you see it defines a wave vector for you, right? Because there is this staggered pattern, you can associate a wave vector to it. If you could measure for an antiferromagnet, the response, this magnetic susceptibility at this wave vector, then you would again see a giant divergence, right? So see, this is already nice, right? Whatever is the order parameter, you couple a field linearly to it and you look at the response, you would see a very big fluctuation near the critical point. Good. So, but let's deal with just this simple problem for now.
Like putting on a field which is
Up, down, staggered. Exactly, right. No, it's very hard. You mean experimentally, right? It's very hard. Because this is some fluctuation on an atomic scale. Yeah. That's why you needed to wait for neutrons. Yeah. Okay, good. Well, now I don't know what people can do, but still, naively, it's very difficult because it's on an atomic scale. Okay. Any questions? Excuse me. So let's study two response functions. So actually the derivation is very easy. So let's see whether all of you can follow it. So let's first derive specific heat. So what is specific heat by definition? Specific heat by definition is this, right? Now we'll prove soon that this is basically related to this. So look at the left hand side. The left hand side is some response, right? You put in a bit more temperature, then the energy increases by a bit and you take the ratio and that's specific heat. What is the right hand side? The right hand side is the, at a certain temperature T, the right hand side defines the fluctuations in energy. So this is a fluctuation, this is a response, right? So now let's just try to prove this relation. It's actually very easy to prove this. So maybe you can prove this. So let me just tell you the steps. The steps is nothing but differentiation actually. So yeah, actually there's nothing here. So let's see. This is by definition, let's say this symbol denotes a configuration. This, right? Okay, now let me pause for 2 minutes and please do this differentiation, right? So, I mean, what you can just use is that 1 by T is beta. I am of course missing some factors of Kb, Boltzmann constant, but let's just say this. And then please convert this differentiation into a differentiation over d by d beta, and then of course it's easier to do it for you. But please just do it and see what you get. I mean, this is very easy. So just do it carefully and then see whether you get this. Hopefully I'm not missing factors of half, unlikely, but just do it. So yeah, let's see. At least some of you are doing it, so I'm happy. So yeah, correct. Of course. But that they should realize, right? I mean, so let's pause for 2 minutes. I'll also refresh myself. Very fine-tuned. Okay, let's take 1 more minute and not too much more, and then whoever gets this, please just tell me.
What the neutron scattering confirmation of antiferromagnetism, there were indications through measurement of susceptibility.
Yes. No divergence, but there were some features. There was an anomaly. That's correct.
So I think near
Yeah. But the sharp demonstration was through neutron scattering, right?
There's no proof.
Yeah, exactly. Yeah, because there was no way to couple to the order parameter directly. Yeah. No, but the stripe would be, let's say, at pi 0. So a field at pi would not couple with that. See, this is a very strict statement. If something has a certain periodicity and some other structure has a different periodicity, there is no way that you will pick up a divergence. Yes. Yeah, but you have to build a macroscopic structure, right? No, but that happens even for a normal ferromagnet. When you heat it up, there are some patches of downspins, and they have all kinds of. Oh. Okay. Yeah. Something else. Has anybody done it? Done? Good. You got exactly this, right? Or oh no, but that's weird. You should not. So you should use this and okay, because okay. No, but you should not get that. Anyway, just try to do it carefully, and this is the this is not hard. Okay, anyway, hopefully you'll be able to do this differentiation, and when you do this, you get this, okay? Good. So now let me also write what is the magnetic susceptibility, and this you can verify at home. So this big M, sorry, it's not very clear from the way I have written. This big M is the total magnetization. I have not normalized it with the number of spins. Similarly, this big E is the total energy. I have not normalized it with the number of spins, right? So these normalizations are important, right? So I have not normalized it here, okay. Of course you could, then you will have extra factors of 1 by n somewhere or something, good. So this guy is what is known as zero field susceptibility, right? So what that just means is you take your sample, you measure the susceptibility, and then you try to extrapolate it to a very small field value, and then whatever is the susceptibility, that's your zero field susceptibility, right? The reason you do that is then this left hand side is just a function of your temperature. So this is another response function, all of you agree, right? This is another response function. Then the right hand side, this I leave as an exercise for you to do, which is slightly more interesting than this, is the following. The right hand side is this. So this is again another fluctuation in your magnetization of the system, right? So this and this, right? So whenever you have a transition like that, a continuous phase transition, well, I haven't defined what a continuous phase transition is, I will come to that. So whenever you have a continuous phase transition like that, there is a certain divergence here when you approach TC, and there is a certain divergence here when you approach TC. Okay, good. And this is related to, these response functions are related to appropriate fluctuations of appropriate quantities. Okay, okay, good. When you try to do this yourself, the only thing you will have to do is, you see in this partition function, you will also have to put a linear term where there is a field and that thing couples to the total spin, and then at the end of your calculation you have to take this limit. But you should get this, it's not very hard. It's slightly harder than this, but not very hard. Okay. Okay, good. So far so good. So now let us look at one property of the Ising model which should make you all very puzzled, in the sense that how on earth can something ever have a ferromagnetization, okay? So what is your Ising model as we just defined there? This is your Ising model. I have not put any magnetic field here, right? So this is my Ising model. Now see, when I discuss spontaneous symmetry breaking of this symmetry, of course I don't want to put a magnetic field, right? Because if I put a magnetic field, let's say I put a magnetic field, I should use some different color maybe. Yeah, white maybe. Let's say I put a magnetic field here. See, I am talking of the spontaneous breaking of a symmetry. What is that symmetry? That symmetry is that all the SI going to minus of SI keeps the Hamiltonian the same, right? Now see, if I put a magnetic field here, this term remains invariant, but this term becomes plus H times summation SI. So the Hamiltonian has changed. So that symmetry is anyway lost because I have put in something which does not respect that symmetry. Therefore, if I want to talk about spontaneous symmetry breaking, I need to cross this out. But you will soon see I have to cross this out in a very particular way, and only then would things start making sense. So, okay, good. So let's say I just cross this out, so there is no magnetic field for me. Okay, this is my Hamiltonian. Then this symmetry is present. Everybody agrees with me? Good. So therefore, this is true. This is true, right? Therefore, if I give you a configuration, with some bunch of +1, -1 and so on, so let me call that some configuration C, right? So the probability, so, and this configuration let's say has a total magnetization M. Then, if I just go to each spin and reverse that spin, I'll of course get some configuration with -M, right? And that configuration will have exactly the same energy as this configuration, right? Agreed? By definition. Therefore, this guy and its partner, this guy and its spin reverse partner would have exactly the same probability of occurrence at any finite temperature. Agreed? Therefore, if you calculate average magnetization, you will, so what is average magnetization? It's just M times e to the minus beta. So there is a configuration label, this, right? So for each spin configuration with M, there is its partner with -M, which has exactly the same weight or same probability, right? So, you know, the sum would therefore be identically 0 at any temperature. Does anybody have any disagreement? I mean, this is very simple stuff. It has to happen. Please just take a moment to see whether you understand it. If not, tell me. What? Oh, repeat. Oh, I see. I said that this is my Hamiltonian. Where was it? This is my Hamiltonian. I forgot what was the last, this one, right. See, okay, when I calculate expectation of M, I am doing this kind of a sum. Forget the denominator, it's just some denominator, right. For each configuration, I can find its total magnetization. Some configurations may have 0 magnetization. Anyway, they won't contribute to this. But all the things which will have finite magnetization will contribute to this sum. But it has always a partner, its spin flip partner, which has -M, but they have exactly the same probability. So if a term with +M occurs with a certain probability, the term with -M occurs exactly with the same probability. So then the sum is anyway 0. That's it. So the sum is 0, just by the symmetry of this problem. So at finite temperature, therefore, so at any finite temperature, T greater than 0, this is true. So does anybody have any reservations or problems with this? Then how on earth do you get ferromagnetism? Okay. What do you mean? Because this is the definition of your probability. I mean, E of C is exactly the same of E of, let me abuse notation a bit, and this is abuse of notation, of course, E of -C. Therefore, P of C is exactly the same as P of minus C. That's the proof. Is that okay? Okay, fine. So then the question is, what is the meaning of spontaneous magnetization? Okay. So let us try to define it properly, the definition, and then we'll see physically what it means, right? But first, let me tell you the definition. So suppose you have a system in which you suspect that there is some spontaneous magnetization. Suppose you have a suspicion, right? You can have all kinds of suspicions in life, right? Then you have to check your suspicion. So in this case, my suspicion is that there is a spontaneous symmetry breaking, and therefore below a certain temperature this thing becomes non-zero. If I have a suspicion like that, I have to take my starting Hamiltonian and then add a term in it with the order parameter that I am suspecting characterizes the symmetry breaking. So in this case, this SI summation is the thing, because if it becomes a ferromagnet, then what it means is things are predominantly up or predominantly down, right? That is what is being characterized here, right? So I put a term linear to it, and I put a number in front of it. In some cases, this term might have a physical interpretation. In this case, the interpretation is magnetic field. In some other cases, it might not have a physical interpretation in the sense of you doing something in a lab. That is irrelevant. Okay, that is irrelevant. You have to check whether the thing is broken, the spontaneous symmetry is broken. Whatever symmetry you suspect is broken, you add a term in your Hamiltonian, which is linear in the order parameter, and you put a coefficient with it, and that's it. That's your new Hamiltonian. Okay, that's your new Hamiltonian. Then, how do you check that something has broken symmetry? So there's a very precise definition. So the definition is this. So I'll just give it in this context. So if there is actually a phase transition, okay, if there is actually a phase transition in your model and you go below Tc, then the following thing should happen. And I'll be very careful in the order of limits here. Okay, I have to take the something's limit first and something's limit later. So this limit is taken first. This limit is taken first. Now let me just denote a shorthand. So you see, when I put a magnetic field, then I am just going to calculate magnetization per spin. So capital M divided by small m, I just denote it by a symbol small m, right? And that magnetization, of course, only depends on two things: temperature and magnetic field, right? By definition, it doesn't depend on anything else, right? So this is plus m naught, and that's greater than 0. Oh, sorry. That's less than 0. So this is the definition. So let's try to understand it. So I apply this quote unquote fake magnetic field, right? As I said, in some cases this field might have a physical interpretation, in some other cases it does not have a physical interpretation. One example, see, yesterday we very briefly discussed about the superfluid, right? In a superfluid, if I try to do this, whatever field I'll get, whatever term with whatever field I'll get, I'll not be able to apply it in a laboratory. Okay, so that doesn't have a immediate physical application, but that's okay. I mean, this is how it's defined and it has physical consequences. Okay, and then first, okay, so you calculate the magnetization with temperature T and magnetic field H, and then you start increasing the number of spins in your system. And then you have to take two limits. First, you take the limit of n tending to infinity. First, you take the thermodynamic limit. And only after that, you take this limit of switching off the magnetic field, right? Now see, here I am switching off the magnetic field by 0 plus. That means I am going to 0 from above. Here I am going to 0 from below. If this model has a phase transition, then I'll get a positive number here after I take these limits, and I'll get a negative number here after I take these limits, and if I'm above TC, I'll get 0 here. That's the definition of phase transition. So that's how you can mathematically define it. And now there is no ambiguity of that. This can happen, and we'll understand physically what this means soon. But I mean, if you directly do this thing at zero magnetic field, I mean, you would naively think that you should always get 0, which is correct. If you naively think about it, that's exactly the answer. But there's something more interesting happening there, which we'll soon discover. So this is the way you should do it. And yeah. Correct. Yes, I mentioned this. So this little m is just total magnetization divided by the, yeah. So the reason I'm doing it is normally it's sort of more physical to look at intensive quantities, but that's it, yeah. Okay, does anybody have any question at this point? So this is a definition, but questions are welcome. Okay, let me ask you a question then. Since you are not asking me anything, I can ask you a question. Let me do this. Let me reverse the limits. Then what should I get? Oh, okay. Why do you think so? Because? Because of that. Okay. So then why is this obvious? This is obvious that why it's plus m and minus m. But okay, we'll soon see what's the meaning of this. But yeah, you're correct. If you are in any finite system and then you take this limit and then take the thermodynamic limit, you'll get 0 identically in all the 3 cases. There'll be no distinction. So this is the definition of spontaneous symmetry breaking. Good. Okay, now let's see what it physically means. Oh, let me also draw a graph, since I have drawn a graph in my notebook. Yes? It's a more general definition. What I'm saying is, you take any Hamiltonian, let's say you have a suspicion that there is some spontaneous symmetry breaking. You need to think of the correct order parameter to characterize that. Let's say your suspicion is, maybe this is not the Ising model which Onsager solved. Maybe this is a more complicated Ising model. Let me make it more complicated. So there is this nearest neighbor interaction. Let me also add next nearest neighbor ferromagnetic interaction. Okay, so this is next nearest neighbor, right? Then this problem is not solvable by Onsager's techniques. Okay, but then let's say I suspect that it has the same order parameter. I just add this term, I do my calculation somehow, and then I take this limit. So this is a general definition. Okay. Suppose you suspect that this ferromagnetic model has antiferromagnetic long-range broken symmetry. You can have that suspicion. Then what do? You do this H staggered, and then this -1 xi plus yi times si. Agreed? You do this, right? Then you do this calculation again. But you will see that there will be no temperature where this right-hand side will be non-zero. So that just proves that this order parameter does not exist for the ferromagnetic problem, right? Clear? So this is a very sharp statement. Okay, I hope it's clear. Yes. That you suspect. Yes. It's a very general definition. And then you have to take the limit of this field to be going to 0 in that particular way. Yes.
So in the very general context, it can be not only given magnetism, it can be any other.
It can be anything. That's what I said.
M0 minus M0 will also be there. Like M0 is different.
Yeah, of course, of course, of course. No, of course. I mean, I have to give an example, right? But this is a general definition. This is a general definition. As I said, even for a superfluid it works. But the term that you'll write in your Hamiltonian for the superfluid, you cannot actually implement it in a laboratory. But that does not mean that the phenomenon that you get out of it is unreal. It's completely real. I mean, people have seen how superfluids behave. So, anyway, good. Has to contain the symmetry.
So this M0 minus M0 is just related to this.
Yeah, that's correct. So see,
Otherwise you get some other number which is
yeah, that's correct. That's true. See, whatever number I get here, I'll get exactly the minus of that here. That's actually a reflection of this broken Z2. Oh, sorry, I used the word Z2, but you also used it once, so I can use it. See, this is a Z2 symmetry breaking because see, what is the symmetry operation here? The symmetry operation is Si going to minus Si, right? So this, if you think of a group, has only two elements because if you do this thing again, you are back to Si. That's why it's called a Z2 symmetry breaking. Okay. So far so good. Everybody seems not unhappy. Okay. So good. So let me just draw a graph to sort of show you the limiting thing. Of course, my drawing skills are limited, but I'll still draw a graph. But this is a very important point. We'll see what it physically means. It actually physically means that there is a notion of ergodicity breaking, and we'll actually see what it means. Again, using something which PK demonstrated, not demonstrated, showed, the Metropolis algorithm. And we can actually get the time scales and everything. So this is the temperature axis, right? And so first I have taken my thermodynamic limit. So I'm doing some calculation for a very big system. Now I have to use all my imagination in different colors, which is very limited, by the way. Okay, I can only find two. Oh, now I have found three. Okay. I'm slightly colorblind though, but okay. That's okay. But okay, yeah, these look like 4 different colors. That's fine. Okay, good. So now I'm trying to take this limit, right? So let's say I have some magnetic field there. Then this thing looks like this, right? You see, at any non-zero temperature, there's always a finite magnetization. Why? Because there is a magnetic field turned on. And the magnetization will strictly go to 0 only at 0 temperature. Oh, sorry, only at infinite temperature, right? And similarly, there will be a corresponding symmetric curve like that. No, what do you mean? Oh, yeah, of course, yeah. Just give me some freedom for, yeah. He's correct, of course, yeah. Starting point is the same, yes. Oh, yeah, that's actually important. Let me not, see, that's why I said I had to draw it like this, and then if I don't draw it parallel to it, I'll lose the shape of the curve. But yeah, you're correct, of course. He's absolutely right. Starting point is the same. Oh, God. See, now it's going above. It's not so easy. Okay, yeah, okay, more or less right. Okay, now suppose you decrease the magnetic field a bit. Now it's, oh no, I should increase. Yeah, because then I'll need maybe MF Hussain to draw this after that. Oh, God. So this is slightly increased. But anyway, good, the point is this, and then you can think of other things. So see, here, here, if you're above TC, you take the limit of all these curves, right? You will see that a well-defined limit exists and it's exactly 0. You take the limit from below. Again, it's well-defined, it's exactly 0. Now you go below TC. You will see that again a well-defined limit exists of all these curves. A well-defined limit exists, but it goes to a non-zero value. If you do it from here, it again goes to a non-zero negative partner of itself. So that's the limiting procedure. Good. Okay. So now you may ask me, why on earth am I introducing this H0 plus and H0 minus definition, and what does it, okay, quote unquote physically do? So what it does quote unquote physically is very simple, below TC. So let's look at it carefully.
So maybe there is a hook, just suggesting. So maybe we can draw there is a homework M versus H, same curve.
Okay, please draw M versus H, same curve. Yes, please draw. At different temperatures, yes.
No, not now, later, I don't know what to do.
Yeah. It's a good homework. Please do it.
I mean, and H should cross 0.
Yes. So then you will actually see this phase transition happening from a different viewpoint. Yes. Okay, good. So now, what is this sort of source field doing? Okay, the reason I called it source field is it's in general parlance, it's actually called a source field. I mean, whenever you couple a linear field like that to something like that, you just call that linear term a source field. Okay. So now what is this physically doing? Suppose you have, you are below TC. Now you see there is some finite magnetization. So now what is happening? That's what this thing is. Now suppose H is 0 plus and you have a huge number of spins. And then H is 0 minus, and again there's a very big number of spins. What is the difference in energy of, you see, remember each M guy has a partner minus M. You remember that, right? Good. So what is the energy of 0 plus, H going 0 plus? Let's say there's a tiny H, so this is H times N times small m. This is just the magnetic energy. The other term is of course the same, because I'm just taking the partner, right? So whatever is the other term due to the J, that's exactly the same. Let's call it curly E, right? And then for its partner, the energy is this, right? So therefore the difference in energy is something like this. Now you have already pushed N to infinity first. Please remember that. You have already pushed N to infinity first. So if M is finite, let's say M is positive, okay, that simply means that you will never visit the minus M partners. You understand that? This is very important. You have already pushed N to infinity and M is a finite number. So basically you will, when you calculate the partition sum, in your definition of configurations, you will never visit the minus M partners, right? So if you wish to think about it, that partition function, when we were doing it, so these are all the configurations schematically on a line, schematically. I'm just showing it schematically. So half of these have some positive magnetization and the rest of it has some negative magnetization. And given any configuration C, I can find its unique partner here. Now, what this thing implements is that below TC, actually, if your initial field is a tiny up magnetic field, let's say a positive magnetic field, then the system never visits these things. It never visits these things. Never visits the minus M things. So you have to change your definition of your, what is your configuration space. Your configuration space is just the states with positive magnetization. So the negative magnetization states never come about. That's the real meaning of the statement. So that's why this is also called ergodicity breaking. Okay, but this still sounds a bit abstract. So this still sounds a bit abstract, right? I mean, okay, mathematically this is exactly what I'm doing, but how do I look at it more physically? So then let me show you how to look at it more physically. Okay, here it is. So this is how you look at it more physically. So this is again an actual Monte Carlo simulation. So remember the last class of yesterday, the last class was mine, second last class, where you were introduced to this metropolis dynamics, right? So again, let's say we do the same dynamics, right? So let's say initially we start with all spins up, right? Some ferromagnetic state, right? So this snapshot is your Monte Carlo dynamics is just running and running and running, right? Or you could imagine some physical dynamics also, but here let's say I want to implement it on a computer, so I run this Monte Carlo dynamics. So then you can just look at how the magnetization changes, because of course your Monte Carlo dynamics gives you some starting configuration, then it goes to some other configuration, so on and so forth. So then you can sort of draw a magnetization curve as a function of time, Monte Carlo time, right? Good. So now let's say my temperature for this Ising model, 2D Ising model is 2.2. Let's say I take it 2.2. Why do I take it 2.2? Because this number is actually below the exact critical temperature 2.269. But it's only slightly below, it's not very much below, but this is already sufficient. Now you see what is happening. Oh, where is the point? Yeah. Now you see what is happening. Let's say you look at system L equal to 8. And let's say you look at system L equal to 16. So what does L mean here? So this is a two-dimensional system. So there are L sites in this direction and there are L sites in that direction. So the total number of sites is L square. Okay, good. So now, as I said, the system started with all plus and there is zero magnetic field here. So of course, if you think in this language, you would expect that after a while all plus will go to all minus, after a while all minus will go to all plus, because that's the only way to make this sum 0, right? Everybody agrees with me? So of course that's exactly what's happening here. If you look at L equal to 8, the thing jiggles here because it is at some finite temperature, that's why there is this jiggle, that's why there is this thermal fluctuation, and then after a while it just drops here and then it again stays here. You see, this is -1 or close to -1 now. Of course, it's not exactly -1 because I am at a finite temperature, and it again jiggles here. Then it again goes up, it does something, and of course, these times are from a random sequence in some sense because this is a random process, right? And so on and so forth. But now, look at the interesting thing. Now I go to a bigger system, L16. So this has 64 spins, this is 256 spins. Now you see this wait time. So it goes here, it sort of drops here, and then it seems to wait a very long time here, right? Very long time here, then it goes here, and then see, of course, there is a distribution of times again here, but on the whole, it seems to wait, certainly it seems to wait longer in either the +1 or the -1 states here than here. That much I hope is clear from the picture, right? Now, if I could go even bigger, then you would see this much more prominently, but of course then you run out of computer time as well. Okay, good. So let's try to understand this time scale physically. Okay, but what I'm trying to tell you is the following. Soon, even if you go to L equal to, let's say, let's not even take a very big number. Let's say L equal to 200 or 100, not even 200. Then the total number of spins is 10000, right? That's correct. 10,000. Yes. I always think in the number of zeros. But sorry. Okay. 10 to the power 4. Yes. Right. Okay. Good. Then what you will see, if you could actually do this, and if you have a very generous institute which lets you run your computer program for however long you want, and the electricity doesn't go off and things like that, then you can make a corresponding graph. You would see that, okay, maybe this thing starts from up. It just stays up, stays up, stays up, stays up, stays up, stays up, stays up on this scale. Then maybe here it goes down. Then goes down, exactly on this scale. Okay. So what is the meaning of that? The meaning of that is, even with zero magnetic field, what happens is if you're below TC and your system is sufficiently large, there is a time scale of flip. Let's call this T flip. Right? T flip is when the predominantly up guys go to the predominantly down guys. This time scale diverges extremely rapidly with increasing system size, And therefore, for all practical purposes, let's say this time scale becomes 2000 years. Then for all practical purposes, I can take 2000 years to be infinity. Remember Feynman's definition of equilibrium, right? I mean, yeah, you understand what I'm trying to say. And also in an experiment, then you would say that ergodicity is broken, right? Of course, ergodicity is not strictly broken. Because if you wait for 2000 years, after 2000 years, I'll see this thing flipping. But that's not a very useful thing, right? So this is the meaning of ergodicity breaking in a strict sense. Of course, this time scale is finite for any finite system, but it can be humongously large, and therefore we see phase transitions in our lab as well. That's the key point. Okay. Now let me just estimate this time scale for you, and then the other things maybe I'll start in the next lecture, or I'll see. And because anyway, I'll see. Okay. Good. So let's estimate this time scale. So I'll give you a rough proof. Of course, it's proof within quotes. So, right. So let's say I have all plus. Right? I start with this state. I'll just draw one more row and that's it. Okay, good. Now I want to sort of flip it to all minus, right? So I claim, and you have to think a bit about this, I claim that the easiest way of doing this is to sort of create a domain wall like this, somewhere in the system. Okay? And then, and then this domain wall just does the following, makes all the spins on the other side minus. Okay? Good. Now I have made this, then you would ask me, oh, why are you feeling so happy? Okay. The reason is, now I can freely shift this domain wall. You see, the energy cost of these processes is just the number of broken bonds, right? This you have learned and seen in several of the lectures, right? Is the number. Now suppose I shift this wall, the number of the broken bonds stays the same. So I am paying no energy cost, so I can shift it. So basically, once this wall is formed, this domain wall is formed, it sort of does a random walk, right? And after it does a random walk, of course, after a while, it can just go here and then the whole thing becomes minus. So that's exactly how this happens. So then, let's see what's the time scale of this guy, right? See, what is the energy cost here? What is the energy cost here? This is an L cross L system. So the energy cost is basically, yeah, please. 1%. Yeah, 2JL, yeah. It's sort of proportional to the linear dimension of the system. So now we go back to what Mustansir was saying. So what is the activation time required for this process? By? Yeah. So the activation time required for this process is e to the by kBt. And after this is formed, it's doing some random walk. So basically, this is a thing of L. So basically, after some time steps of, so this is, let's say, a fast process. Let's call this the slow process and this is the fast process. So you can see in the picture, there are slow processes and fast processes. This is obvious, right? I mean, of course, there are also very fast processes. Ignore those. So they're slow and it's fast. The fast is basically a random walk of this, and so that it goes from somewhere to the end. That sort of scales like L square because it's a random walk. Or
multiplied by diffusion constant.
Oh.
That diffusion constant in this case will go like 1 over L.
Oh, I see. Oh.
Because the whole thing has to shift.
Oh yeah, that's correct. Oh yeah, I didn't realize that. Okay. Yeah. Okay. Thanks. I didn't realize that. Oh, so you're saying, I see. So you're saying because the whole thing has to move, it's
not hard to show that it goes as 1 over L.
I see. So the entire thing is order L. Okay. Okay. LQ. I see. Okay. Okay. Good. Thank you. So you could see that my proof is clearly not a proof, but it's almost a proof. Yeah.
Q is still much less than
Yeah, that's correct. That's why I can still call it fast. Okay, good. So you see, now you can see what's happening. Now let's say you take a 100 by 100 system. Put 100 here. This is in an exponential. You can imagine how big this time scale is. Put 1000 here. Exponential of 1000. You can imagine how much bigger this time scale is, right? So then you can imagine what is going to happen here. This thing will stay here, 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 here. Go on, go on, go on. Cross this wall, cross this wall. Then I live in Narendrapur, I'll go to Narendrapur, and then, yeah, I'll do something. So, right. Then, of course, if you increase L, all of you can reach your destinations by following this, wherever you live. Even the moon, even the end of the universe. Actually, that's true. Even the end of the universe, right? I mean, just take any L you want, which is large enough, and you will surpass all the big numbers that you know. That's obvious, right? Yeah, that's what I'm saying. No, somebody might be, somebody's definition of big might be different from your definition, right? That's all. Again, it's a relative thing. So I'm saying, that's it. Good. So see, we have therefore realized what is the exact meaning of ergodicity breaking, and this procedure, this mathematical procedure, exactly implements that, right? But this is a very physical effect, as we have just argued. Okay, good. And that is how phase transitions happen, right? Good. So I don't think I should start with the next thing. So in the next lecture, I would just So in the, just 1 minute. Don't be impatient. Okay. So, right. So in the next lecture, therefore what I'll do is try to, so PK has already discussed 1D Ising model in a different way, in the transfer matrix way. I'll discuss it slightly differently vis-a-vis the role of entropy at finite temperature. Then I'll quickly go to 2D, and then I'll go to some concordant model at infinite dimension, which is called mean field theory. But this is a very, very useful thing to do and to learn and to teach others. Therefore, I'm going to do this. Then we'll try, if time permits, to exactly calculate TC for the 2D Ising model. So then you'll believe that whatever I'm saying is not untrue, right? Okay. So that's the plan. We'll see how far we go, and yeah.
Oh, no, just so for the D dimensional one, the same kind of.
Of course. Correct.
Then D equal to 1, you don't have a phase transition, is visible because it's just a number.
True. That's exactly my entropy argument.
How are you doing that?
Yeah, that is correct. But PK's point is correct. Let me just raise it. Yeah, you're absolutely correct. See, what PK is saying is, suppose you make this thing 3-dimensionally. Suppose, right? Let's just worry about this big time scale. Let's not worry about the smaller time scale, because I'm sure I'll make another embarrassing mistake of some power of L. So let me not worry about that. But anyway, this is the thing I'm worried about. So suppose I am in a cube. Cubic lattice, right? So then, of course, your domain wall may look like something like this, some object like this, right? Where there are pluses on this side and minuses on that side. Now, can somebody please tell me, so this is again L cross L cross L. Can somebody please tell me what is the energy cost of this domain wall? 1 L square, right? It's proportional to L square. Yeah? Therefore, in general, it's proportional to some energy coefficient times L to the D minus 1. Clear? Right? Good. So, what does that mean? T slow is divided by KBT. This is the slow time scale. Now, of course, we saw what happens for D equal to 2. Therefore, for D equal to 3, the divergence is even faster. But let's put D equal to 1 here, then this L vanishes. Then this time scale is some finite number. There's nothing slow about it. You just cross that finite number, and then of course you'll see the flipping. That proves that there is no phase transition for these kinds of discrete models in 1 dimension. So that's a proof. Okay, good.
In that case, T fast will determine how long it will take. I mean,
That's correct. in some sense, right? Because this guy is a finite thing, but this guy is the, yeah. So I'll still therefore do the entropy thing. But you see, at least there is no diverging slow time scale. So it's highly unlikely that there will be a broken ergodicity. And as we discussed, broken ergodicity is necessary to get a broken symmetry. Because this thing is mathematically implementing broken ergodicity. Sorry, ergodicity breaking, not broken ergodicity. Right. Okay, thank you. But please, if there are questions, I am happy to take them now. Also, in the afternoon, before I start, I'll ask you about the exercises, so please do them. Don't think that I've forgotten about them. Okay, good.